Good afternoon, everyone, and welcome to the QBEST webinar. And today we're doing cold room energy efficiency with Ryan Dillon from the Websters group. My name's Andrew Chamberlain from Queensland Farmers Federation. I'd like to welcome Ryan. Hello, Ryan.
Hey, how you going, Andrew?
Excellent, thank you. Great to be here. Thank you for your time again today, and welcome to Jonathan Mendez from the QFF Energy team. Hi, Jonathan.
Good morning.
Thank you. Great to have you both here. So today we're talking about cold rooms, and this is one of those great topics that covers all the sectors that we've been working with in the QBEST program and also in the EnergySQ program. A lot of farms have cold rooms or cooling, so hopefully this will be really useful to a lot of people. Just a couple of little housekeeping things. As people join, you'll be muted and video off, and that's to help us with bandwidth and everything. But if you have any questions or comments, please feel free to use the Q&A box at the top of the screen. You'll see a little Q&A icon. Please feel free to add questions or comments to that, and we'll try and pick them up as we go along. It is being recorded, so as we go through, we'll be able to put this on the QFF Ag Energy Hub website for people to see afterwards. So just for people on board to be aware that it's being recorded. And yeah, we'll post this within a week or so on our Ag Energy Hub website. So just a quick intro, just a quick summary of what we're doing. So we'll just have a couple of quick minutes of me giving an intro. Then we'll have the really good stuff, 30 minutes of Ryan doing a presentation. There's plenty of time allowed for questions and answers with about 15 minutes, and then just a couple of plugs from me for the next webinars in the series and a few other things we're doing here at QFF. So without further ado, I really want to keep this short, but we'd love to jump straight into your presentation, Ryan, if that's okay with you. Thanks. Oh, hang on, I'll just introduce you properly first, eh? So QBEST, it's the Queensland Business Energy Savers Transformation Program. With this program, which is delivered by QFF with funding support from the Queensland Government's Department of Energy and Public Works, we're doing 35 Type 2 and 3 energy audits on large farms throughout Queensland. So that's farms that use over 100,000 kilowatt hours a year of electricity. And we're also consolidating all of that information along with all of the other results and case studies from other audits that we've done on the Ag Energy Hub website. And I'll give you the link to that a little bit later after Ryan's presentation. And I'll just quickly talk to you about farm energy efficiency rebates that do pop up from time to time. I'll do that at the end of Ryan's presentation. The presenter, Ryan Dillon. Ryan's the managing director for Websters Group. They've done lots and lots of energy audits for us as part of the QBEST and various other energy programs that we've run. Ryan's been to loads of farms with cold rooms, and so he's got some really good experience on cold rooms and cooling systems more generally. And he's also been a runner-up in the Energy Efficiency Council Award for the Best Ag Energy Efficiency Project, and it was a horticulture farm as well with some cooling facilities up there. And he's been featured in QFF's Energy Audits and Jelly Beans webinar, which we did a couple of years ago, where Ryan presented us a jelly bean for, it was every dollar of energy savings that you identified in the audits that you did under the previous program, Ryan. Is that right? $1 or $100?
$100, and there was 138,000 in savings, so a jar about this big of 1,300 plus jelly beans.
Right, well, thank you very much, Ryan, for joining us, and I'm just going to hand over the screen now to you so you can present.
Thanks, Andrew, and thanks everyone for joining.
Just going to turn
Is that in presenter mode there, Andrew?
Sure is, Ryan. All good.
Great. So cold storage, as Andrew has mentioned, we've done a number of Type 2 energy audits to the Australian and New Zealand standard 3598/2014. And at a Type 2 level, we're looking at a medium accuracy, which means that we've put in various motor runtime counters, temperature data loggers, and performed measures to have some accuracy in regards to some of the recommendations presented. and they're in a Queensland context based on energy tariffs from 2024 at some of the SME agricultural sites we've had the privilege of attending. So Andrew just mentioned QBEST, and the word transformation comes to mind because we're certainly at a juncture with some of the emission reduction targets and the journey we're going on towards net zero. Now, there's around 260,000 walk-in cold rooms and freezers in Australia, and that's equivalent to around 4,800 gigawatt hours of electricity use, which corresponds to about 1.75% of Australia's annual electricity demand. And quite often that demand's quite wasteful, where, as demonstrated through these audits, where there's been sufficient rigor through data logging and monitoring and measuring, we've seen upwards of 30% reduction in sites with cold rooms through energy efficiency and renewable energy, where over time, through retrofitting and smart design choices, as you reach end of effective life and start to plan for the next generation of cold storage, and that being more efficient, we can actually see anywhere from 30 to 50% reduction in energy use, where that quite commonly has an investment grade return on investment. So what I wanted to do via the webinar today is actually drill down into energy efficiency, given that's what we really have to address first. Quite commonly, it's a simple call to action around putting solar on the roof to reduce the energy bill, but where that's powering this waste and we haven't addressed this efficiency first, you'll find those systems are quite commonly oversized, and that capital could actually be better addressed through energy efficiency, whereby you achieve a higher return on investment. So this is a 101 to refrigeration with a few rules of thumb to get out there, have a look at your cold room and understand what the energy consumption for each of these segments of use is. And when we're talking about cold rooms, what we're really talking about is rejecting heat and understanding heat loads. So if you have a refrigerated product in effectively a box, which is a cold storage facility, what are the energy demands and what heat's in there that you have to reject? So we have the product load, which is where you have, say, a crate of broccoli coming in at the field temperature or ambient temperature, say that's 20 degrees. You're trying to drop that to 2 degrees. That has a certain amount of electrical energy use. Once that's actually in the cold room, and say, for instance, that's stored for 6, 12 weeks, or also you've actually got the losses in the building envelope, which is the walls, the roof, and the floor as well of the cold room. The fans that operate the evaporators that circulate air, cool air across the product to cool it, have an energy consumption, and the air infiltration that's through the door strips or just leaving the door open, hopefully not for too long. These are the examples of where energy is consumed in a cold room. So I'm going to go through each of these and some simple measures you can do to address each, while also giving you an understanding of the order of magnitude and how important some of these areas are relative to the other, so you know where to actually spend your time when reviewing opportunities to improve efficiency. So a key distinction, as you can see in this table here, is whether you have a low turnover or a high turnover storage facility in the first two columns there. Now we have in the left-hand column the product load, the fans, the envelope, and the immediate thing that stands out from here, if you can see my mouse, is that cooling the product initially actually has a reasonably low energy use compared to the losses of the system over a normal year. And we'll really drill down into that. So just addressing those product loads and that up to 5% you'd normally see in a low turnover or a high turnover room, it's really dependent on the product. So you can see here a few products and what we call the specific heat, which is the energy required to change 1 kilo of product by 1 degree. And here you can see, for instance, we've got carrots requiring 3.81 kilojoules per kilogram. And if you were to have avocados, that would use less electricity because there's less heat demand to actually chill that product per kilo. So the cold room design is really product dependent. And if we were to just put that in broad metrics, and this changes from product to product, but at a very general rule of thumb perspective, from a type 2 audit we recently completed, we had around 45 cents per crate of broccoli to take it from that ambient field temperature. The site's located in Gatton, down to 2 degrees. And you can see on the right-hand side here, this is just a thermal image of some broccoli in the cold room, just showing the temperature. But just as a rule of thumb, 5% of that energy use in a cold room is typically associated with cooling the product initially, getting it to temperature so that you can cool it and keep it cool in the cold storage there. So moving back to this table, your biggest bang for buck and the highest percentage of losses or heat gain into the room, given you're rejecting heat, is through the building envelope. And I've just presented that in a chart here, and you can see with the low turnover storage, say for instance, you've got seed potato and you're storing that, the losses through the envelope are a lot higher. The product load, initially cooling it, is a little bit lower because you have low turnover storage. It's mainly product going in there and staying there for longer periods of time, as opposed to crates coming in and out and in and out. So that's just a comparison of a high versus low turnover storage. But the key message here is all about the building envelope and the losses over the year. So we can see here the front wall of a cold room on the left-hand side there with the door. And I was here at 9:30 in the morning, and we have the eastern wall and the growers just putting some crates there to actually shade the wall. But when we look at it with a thermal camera, what we can actually see is the incident sun above this roof at that time in the day, creating a thermal gain, and that creates a load that the cold room has to deal with. If it was all shaded, you'd have a lower load to actually deal with, and you can see this difference between what's shaded and what isn't shaded. So the strategy around locating the crates, dependent on the cold room location, you have to access it. You can't always address and shade a cold room. But here, through the 2 temperature measurements for a calibrated thermal camera, we can see almost a 15-degree difference between the shading and that incident sun at 9:30 in the morning. So what does that cost per square meter of wall? Well, from this site in Gatton, and this was to a type 2 audit standard, we have $12 per square meter per year shaded, or $19 if it's this eastern wall and it's left exposed. So quick rule of thumb to measure your cold room and start to think about what does it actually cost per square meter. And this is for 150 mil thickness wall. Something else to consider is the roof. So if you're in a tin shed and you don't have insulation, that hot tin roof, dependent the distance between the top of the cold room and the roof, can have a heat gain. And if you were, for instance, after you've addressed energy efficiency, considering solar energy, actually locating the solar above the cold room can help in reducing that heat gain if you haven't insulated the roof. And with a thermal camera, you can actually see each individual panel and the effect of this. It provides a genuine cooling effect. So instead of installing insulation, you can also consider the use of solar energy and the location of that to assist in reducing the thermal gain to the roof if you have a cold room in a shed. Now, I'd mentioned these crates before on the eastern side of a cold room. There's actually a door there. And when we're talking about the building envelope, it's not only the insulated wall, but it's also the rubber seals, given there's not much insulation in rubber seal. And you can see that in this instance, the incident sun's hitting that seal. And this is just the thermal gain from radiant heat, not the air component coming through the seal, just the radiant heat is 9.5 degrees and proportional to X square meterage of wall. That's equivalent to a certain square meterage of wall in effect, because you've got a pretty high heat gain where you've got the door seals that are exposed to direct sunlight. So just something to be mindful of. And that's kind of a summation of where we're looking at these 50 to 70% heat losses that need to be rejected year on year in your cold room. So I'd mentioned the door strips just prior. They have that thermal envelope and the radiant component, but if they're not providing a correct seal, we also have air infiltration. And on an order of magnitude, we have air infiltration over here, and that's both the door seal as well as the number of doors opening. So this might have a low number of doors opening, and this might have a high number of doors opening. So you can see the seals are a suitable component of the actual infiltration losses that need to be dealt with. And you can visibly see it with a thermal camera. Here is the seal, and you can see this striation, or this pattern, sorry, of the air actually flowing out of the cold room and chilling the concrete. So we know there's an air infiltration issue. Quite common, anything with a visible air gap or seeing sunlight through the door is a problem. So go into your cold room. Is there a visible gap? And then through the use of thermal imagery, if you were to do a type 2 audit, for instance, you can then further refine and pick up some of these problem areas. Also looking for holes and other gaps in the wall, or where you've had a system integrity issue with the cold room structure itself. There might be some air infiltration that you can address through seals in pipes with evaporators, for instance. But from a seal perspective, and this is conservative, looking at a site in Gatton and a Queensland reference point, it's around $18 per metre of seal, at least, for a faulty door seal. So at least $18 per metre. It isn't expensive to replace. And if you think of measuring a door, you've got the height and the width. So you've got 4 sides of the door. You find the meterage, multiply it by 18, you'd have savings of at least that. If you've got visible gaps where you see sunlight through, it might be much more than that. So in terms of infiltration, we not only have the door seals, but the door openings is a large heat gain, as we've seen in the chart looking at the low versus the high turnover. Now at site, this door was left open for about 20 minutes, and you can see here, just through the air infiltration, the front crates are starting to warm. Now what happens with a door is that the cool air comes down the bottom half of the door and the warm air flows through the top. The evaporator fans are mixing the air throughout, and it provides, there's just general warming in the room when the door's left open. So some ways to address that are to install plastic strips, as you can see here. These strips do have a few holes in them, so it's not a complete barrier as such, but it is helpful. So maintaining the strips is key, but also considering the amount of time the door's open is super important. So to put a number to that, quite commonly when we do a type 2 audit, data is so valuable, and the estimate of door openings is quite difficult to determine. Quite often you go to site and you ask the question, how often is the door left open? And you might come up with a certain number of openings, a certain number of minutes per day. The best way is to actually measure it. So if you have a rapid door or a motorized door, we can install a motor runtime counter. And this actually just measures the hours and minutes over, say, a month that the door actually was open. So you have not only the number of door openings, but the length per door opening. You can also use light sensors, and we have light sensors that we use where the door opening triggers the light switch, the lights turn on. We measure the light because that's a little bit more reliable than trying to create a mechanical switch on the door to show it's open, because sometimes it might be not as accurate just based on our field experience. So there's a few ways to use data loggers to look at door openings, and that's key, because what you don't measure, you can't manage, and having something accurate at a type 2 level, I mentioned as at the start, under the Australian standard, we need to hit what's called medium accuracy. So we might monitor this for a month and try and get some real data on door openings. And what we've observed from those audits is a blended average kilowatt hour rate across different sites. Each site's different. So we had a range of around $7 to $15 per hour in electrical cost per hour that the door's left open. Now, for using plastic strips, if they're in good condition and they're well maintained, that can actually reduce that cost by around 85%. And it's not only the fact that you've got a plastic strip there, because that sits behind the door. You can include door alarms, for instance, to help change the culture and help educate staff with just a flashing light or a flashing light and sound if the door's been open for, say, 20 minutes and you know that you would normally not have it open for more than 15 minutes. It's just a way to provide a visual cue to just help change behaviour. And that talks to some of the air infiltration. And something that's important to keep in mind is these are design calculations. So while we know product loads reasonably small, air infiltration might be next, and envelope losses are the highest, if you actually have staff behavior that really, leaving the doors open, having the forklift run in and out, no door strips, and it's just left open while someone's on lunch, that usually doesn't happen, but if it's excessive, you can see, pretty reasonable increases on the design basis for how these bar charts go up in each of these segments. So this is a design basis. It's just something to keep in mind when looking at retrofitting a cold room. Now, fans in cold rooms, pendant the efficiency, consume a certain amount of electrical energy. But when you take a thermal camera in there, you can see they're also a heat load. So irrespective of the efficiency of the fan, you actually have a heat gain attributed to the fans. So we want to target what's called energy productivity, which is where you use a higher efficiency fan. So the fan provides more mechanical airflow, so you don't have to run the fan as often, because anything consuming an electrical load in a cold room, whether it's a light or a fan, pretty much all of it turns to heat anyway, which then needs to be rejected by the refrigeration compressor in the refrigeration cycle, which costs money and electricity. So designing for efficiency also relates to airflow and how you stack the cold room. So you can see here the airflow patterns from the fans. These are the lights, which are put right in front of that, so that maybe you could put them elsewhere, or you probably wouldn't, because that's where the aisles are and the airflow is. So you need to consider how these things work together. But in this instance, you can see with the stacking of the product, we have a bit cooler and a bit warmer. And when we're measuring airflow, it's attributed to that airflow. So in between the crates, we have here an airflow of 1.45 meters a second at the back of the room, whereas kind of tucked in the corner, you have 0.84 meters a second. So designing for efficiency, perhaps getting a simple thermo anemometer or an airflow meter is a good way to just test your room, just understand what's happening, and obviously not running the room to chill the crate in the corner and over chilling the product, because that's loss in and of itself as well. Other loads to consider are forklifts. If you've got in combustion engine forklifts, you can see here that temperature is quite high, and it's not only the temperature going into the cold room, but it's also the particulates being trapped in that room, and then the evaporators sucking that into the evaporator fins and soiling the evaporator fins. And you can see that in rooms with a lot of forklifts, because the evaporators have a lot of soot where the airflow is, and that just means more cleaning or new forklifts, but it reduces the efficiency of the evaporators if they're not maintained. And forklifts coming in and out, while there's not much you can do about that, it's something you need to be mindful of from a design perspective. This is a funny one, people. Now, people emit radiation, and I did some quick calculations before. An average person with an average metabolism, because there's a resting and an active metabolism, on average, you'll actually emit around 200 watts of heat as a person. And I'd recently turned 40, and I was just thinking, how much heat have I emitted in my life? And I looked at how much an average house uses. It's around 5,500 kilowatt hours. And if I was able to bottle up all that heat over 40 years and convert it with 100% efficiency to electricity, it would run an average house for 10 to 12 years. So while there's nothing you'd do about this, it's just something to be mindful of. It is included in refrigeration design calculations, where in this example, you've got a picking and grading line, you've got a number of people in there. It's around 5 LED lights equivalent, and just something to be mindful of in terms of when you're designing a new facility. But just an interesting fact, something to get you thinking about thermal loads in cold rooms. Thinking outside of the box, literally outside of the refrigeration unit, now that we've dealt with a lot of the heat loads, are some of these system issues, and particularly where you install chiller units. So here you can see a chiller unit where on the right-hand side, It's reasonably close to the wall, and then you've actually got a higher air gap here. And in that design, there were some fans installed in the roof to reject that heat that comes out here. So when we run the thermal camera across this, and you can see the fans here to reject heat, there was a purposeful cut in the roof. Despite this, what we're seeing is as that heat's rejected, it is cycling this way. As it pushes up, some of it pushes back down into the condenser vents, and there's a bit more room on this side. So what we did, given type 2 is all about accuracy and trying to identify with real measurements what's happening, we put a temperature data logger on the right-hand side of the condenser and one on the left-hand side, because the working assumption was this is a bit more constrained. We think there's a higher amount of airflow sucking in that way versus this way, because we don't think these fans and this hole are effective in rejecting all of that heat. And the results came in with this just being 1 day and a little bit of the morning and the afternoon of another day. 1 day we can see the ambient temperature in blue. The right-hand side, which had the bigger air gap between the wall, is a bit higher because there's some recirculation of air, but it's that left-hand side that's a few degrees more, or in this instance, that's a 5-degree temperature delta. So, and particularly in summer, that's something to be mindful of because this increases your energy use. So the low-hanging fruit in this scenario is just how do you get more air out of this room? But it doesn't necessarily stop there because the cold room's on the other side of this wall. So you have temperature gain through this building envelope concept we talked about with the 12 versus the $19 per square meter component of a cool shaded versus a hot wall with sunlight. Like this is the same concept where you've got a higher ambient temperature creating higher heat gains for the building envelope. Strangely enough, here's those chillers down here. In the same roof area, in the higher area where the heat rises to, there's actually a hole in the wall where conveyors go through. And what we're seeing here is that while the cool product comes in, it's the actual belts that are warming up because they're exposed to that temperature. And there's also an air gap over here where that hot air's coming into the system. And this is a virtual cycle where then you've got this warmer air coming into the room that needs to be rejected by the system, which then generates more warm air, where we actually just reject that air quicker. And with a higher airflow, we reduce the ambient temperature, which reduces the coefficient of performance of the, increases the coefficient of performance of the unit, which means that it's more efficient. So with that as a summation of efficiency, it really is something that you can deal with, and just thinking through from those principles, hopefully that stimulated some interest and intrigue about how to have a look at cold rooms and think from first principles what to actually do. Another key consideration more for medium to larger cold rooms is not only how you use efficiency and then renewable energy to offset use, but how you shift your load. Now, I was looking at AEMO this morning on the current energy forecast, and the forecast for now, and it just turned to 1:30 New South Wales time, 12:30 Queensland time. In the Queensland market, the spot price as of this minute is currently forecast to be negative. So that means at negative $45 per megawatt hour, you're being paid 4.5 cents to consume electricity. So yes, cold rooms, if you were to load shift, would be paid to consume electricity right now, as opposed to later in the day, where the forecast was $350 per megawatt hour or 35 cents a kilowatt hour. So if you are able to load shift or pre-chill your room a couple of degrees and use in a larger room this concept of thermal inertia, the grid rewards you if you have a spot market exposed contract. Now, a normal energy tariff and normal energy contract will incorporate these changes in hourly, half hourly, 5-minute pricing. But if you were to be in a more advanced, sophisticated type of contract where you're exposed to the market, if you had this level of control, you can actually really benefit from, and today, be paid to pre-chill your room and avoid some of the larger spikes. A little bit more of an advanced concept, but certainly something on the radar worth considering if you have a medium to larger cold room there's some providers that operate and some software that can be used to forecast, and happy to discuss that offline. But given cold rooms use 1.75% of Australia's electrical energy use, if you have a medium to large room, not only thinking about energy efficiency and avoiding costs, or load shifting and avoiding costs, with our 2030 interim targets, and if you have organisational sustainability or emission reduction targets, the actual time of use of when you run a cold room is equally important, given each hour of the day has a certain carbon emissions profile, and energy at the middle of the day, for instance, might have a little bit more solar, so lower emissions than after hours electricity. So where you combine the load shifting with an emissions reduction perspective, you might actually find that cold storage really is an asset in your decarbonisation journey, if you have a portfolio or several sites and are at that scale. And equally, if you're at that scale, something to explore is demand management. I won't go explicitly into detail, although this actually generates revenue in that you're reimbursed for turning off or load shifting cold rooms for minutes, seconds, or hours. And that's how cold rooms with that concept of thermal inertia can not only become more efficient or load shift, they're also really important if you have a large amount of cold storage in your portfolio of sites or several sites. It's just a different way of thinking of them as an asset, in that you can not only cut the cost, but can also generate revenue from turning them on and off and load shifting and working in more sophisticated types of energy contracts. So a lot of audits that we've completed, as Andrew mentioned, had cold rooms. It's not uncommon to find 38, 46, 58% reductions or significant reductions in energy use where you have cold rooms on site. So the main message is use some of these benchmarks, get involved where it gets a little bit more sophisticated, and you want to look at the design of a new facility or how you can conduct a deep retrofit to get these kind of gains. You'll find an energy audit is quite helpful. An energy audit gives you that expertise. It helps you address strategic risks and fix problem areas. We're targeting at least a 15 to 30% reduction. And quite often, as demonstrated in these case studies, you'll find the savings of the audit often significantly outweigh the costs. So thanks for listening and talking all things energy efficiency and cold room. I hope everyone isn't overwhelmed and enjoyed that. And I might just pass it back to Andrew and let's have a few questions.
Okay, just gradually getting it back, Ryan. That's fantastic. Thank you very much for that. I'm just moving back to the slide. Yeah, thank you. That was great. And look, it was the highlight for me there was just having dollar figures on some of those things that we see every day when we go to cold rooms through QBEST and through EnergySQ, like door seals and open doors and exposed cold rooms. Just being able to put a dollar figure on that, so people that are listening can walk back out to the shed a bit later on and really know what a door seal is costing them per metre, and an hourly rate for opening doors and those kind of things is fantastic. I also wanted to ask you a quick question about the load shifting, because it's very valid to talk about and understand what the market prices are doing and how the price increases rapidly in the evening, but also on days where there are blips or very high demand issues in the network. But also just wanted to say how relevant that is, and perhaps you could comment, Ryan, to people that do have solar systems, when the solar system might start slow down its generation in the late afternoon, so that if people do have good cold rooms that have good seals and are able to keep the doors closed in those evenings, they might be able to, the cold room condensers and fan units might actually slow down in that evening period and use less power in a good quality cold room. Would you comment on that, Ryan, please?
Yeah, for sure. I suppose we can kind of see that matching principle in that chart where we had the daytime temperature of the chiller, and you can see that diurnal, that hump pattern. I haven't explicitly measured that with current audits we had, although it's a really relevant principle in terms of what percentage of electricity comes from the grid at what time. And that time of use efficiency component is really key. So having, from a simplified perspective, just your solar portal commission to be able to just log in and see the data would probably be the first step. And then having some energy sub-metering or smart metering to really identify that. It's probably possible you can just manually look at that and get a feel for that at a very basic level. And then playing around with load shifting, I mean, it's a really rule of thumb farmer kind of forecast. If it's a sunny day and you know the product's coming in at 2 p.m, maybe you just pre-chill the room because you know you've got excess solar, jump on your app and do some things like that. So there might be a really simplified way to do that just with the solar app if you've got solar, just being mindful of your production and how you can utilize solar as a resource as such. So that's an excellent point, Andrew. It's again, it's all data related, right? So if you've got solar, go and get your inverter portal set up, and the inverter portal is typically just a login that you can have a look at on your app that just shows instantaneous generation and whether your production's in excess of your site usage. So that there might be a really simple way to do a bit of load shifting if you have a bit of solar already.
Yeah, excellent, thanks. And then, you know, as the day winds down, you know, the heat tends to drop off as well as the solar generation, which is obvious, but you know, you may decide to leave the doors closed after 4 p.m, for example, to stay within your solar generation envelope. Make sure that the condensers and fans are being used as little as possible after that time. We don't have any questions from our listeners, Ryan. You've explained everything so well, but I'd just like to add that you know, how powerful those tools that you are using in those audits, like the runtime counters and those thermal imaging cameras, just really let you crystallise. It's just clear to see where the efficiencies are or the inefficiencies are. So that's excellent information, and to be able to highlight that to people, just the difference in the heat load on the outside of a cold room that's exposed even to the morning sun, and even in the August to October timeframe, which you had highlighted on the bottom of that as well.
I think some of the interesting insights that have come to me out of the cold room is there is a limited ability to retrofit cold rooms in terms of those low-hanging fruit. Put a shed on this side of the wall, put in curtain strips, put in new seals and such. You're then starting to think about, hey, we might be moving from this facility. How do we design a new cold room? The audit can add a lot of value where you actually get real measurement of door openings, for instance, or you've actually gone to a medium accuracy to actually get some data, because then that can be given to a sales engineer or to a provider supplier to size and design the cold room better the next time. And you can understand those trade-offs, appropriately size it, not over-engineer it, hopefully save some cost in the process. So my perspective is that it's not only about the retrofit of the existing cold room, but thinking about the effective asset life of a cold room.
Yep.
And something that I didn't include is that there are textbook values and journal articles that look at the building envelope, given that's one of the larger components, and how that deteriorates and what uplift factor you'd provide to a large cold room for a wall. And some of those figures are like a multiple of 2.6. So if you think of the age of the actual building envelope as that ages, some of those nominal journal articles that have examined new versus old, it's quite interesting to just think about the building envelope and what the total cost of ownership of a cold room is and how that cost kind of increases as it ages and deteriorates. So there's limited benefit to retrofit, but then getting the data, thinking about not like for like replacement, but with that data, how do you design something a lot more efficient, is an interesting question as well, so that you're planning for the future and not just replacing the chiller when the system basically just reaches its end of life. You're not just like for like replacing. Like, you really do have to be prepared to know what model you need to replace with and what it's going to cost, so you can pull the trigger on it. Hopefully not last minute. Like, you might need to make a preemptive kind of call on when is the total cost of ownership kind of worth transitioning, and not waiting till it blows up, basically, to then lock yourself into the next cycle of having to stick with that chiller and that cold room and those energy costs ultimately.
That's right. I mean, I think we saw one of the energy audits that we did earlier where there was I think a payback period of about 8 years on the upgrade of all the cold room fans and condensers, which the farmer said was outside their target range for investment. However, it was a fairly old system, so they kept that audit report in the top drawer, knowing that the cold room was probably not too far from end of life. So they had the specification there for when that did happen, or when a grant program came up and they could afford the upgrade. So it's a good point, and if maybe we could finish with a couple of points for if you do have a cold room and you're thinking of adding another one, or you don't have a cold room and you're just about to install one. What are your top couple of tips there, Ryan? Given what you said about the envelope, a couple of top design tips for a new cold room.
Put it in a shed. We saw the thermal image of the heat gain and the $12 versus $19 per square meter for exposed versus shaded. And if you've got two cold rooms, put them side by side and utilize the same wall, because then you've eliminated effectively, if it's a square, 25% of your heat load gains on each room, because you've got a shared wall, provided that they're running, the same time and at the same temperature. It's just a logical kind of, can you utilize the existing wall, join them together, because then you're actually literally cutting your energy use by sharing the wall, so there's no heat gain, if that makes sense. So yeah, put it in a shed and just think about how you configure it, probably would be the quick top two.
Right, and also airflow for those condenser units, and good shading and airflow.
Of course, sorry. The case study from the last webinar, I'd mentioned a couple of degrees temperature differential. We had something that was really packed tight into a shed for a milk vat, and there was a 10-degree temperature differential. So yeah, from the case study today, even 2 degrees with fans installed like it was designed, but it probably wasn't tested until you put the thermal camera and see there actually is, or a temperature data logger, there is that as-built difference between the design, and it might be interesting to just think about commissioning then as well. Like, yes, put it in the right location, designed for airflow, but with your supplier through your contracts, can you think about the target efficiency and have some involvement in the commissioning phase to just check it actually is performing as specified. So yeah, many things to think about. So, and finding the right supply is key. So getting references, designing for efficiency, understanding total cost of ownership are key, because quite often if you're buying something cheap because it's broken and it broke last week, you're paying for it through the energy bill over the effective asset life. So it's weighing up the CapEx or capital expenditure versus OpEx constraints, and ultimately, having a more efficient site, improves EBITDA, bottom line performance, gives you the ability to loan more funds or just have a more profitable, sustainable business. So it's efficiency in cold rooms really hand in hand with business productivity, and the dollar per crate you're packing and getting out the door, where efficiencies just go straight to the bottom line. So you kind of lock a lot of that in through the design, right? So
yeah,
it's just something to be mindful of.
it's a great point that some of those other benefits, like you talk about those other financial benefits, but then you know, people with good cold rooms talk about things like more or predictable temperature control, and then things like I was at a place in Mundubbera where they've got very good cold rooms and they lost power for a good amount of time, and the temperature in the cold room didn't drop below a critical level for them. So you've got all those other benefits for having good cold rooms.
That is an interesting point, actually, because you could resilience test or almost spot check that performance, and that's part of contingency and managing risk. If you don't have a generator, is to just actually do that as a test. So, you know, experimenting with your cold room is really important as well.
Okay, I might leave it there in the interest of keeping the video nice and short for people to watch afterwards. But thank you, Ryan. That's been brilliant and really good information and great evidence to support the discussion points around, you know, the thermal imaging camera and runtime sensors. I mean, it's just great level of accuracy. I'd just like to finish by talking about a couple of the programs that Jonathan and I and our colleague Sam are running here at QFF. There's the Queensland Ag Energy Hub, and that's where you'll find this video in the next week or two, along with some of the other webinars we're doing, which I'll talk about in a second, and Ryan's dairy energy efficiency webinar. So there's loads of fact sheets, case studies, efficiency tips, and resource and financing options, including any grant programs that are current at the time. And you can search by sector, technology, irrigation, location, and all those kind of things to find the case study or the information that's right for you. We're also working on a program called EnergySQ, working with farms in those 6 local government areas: Southern Downs, Gundawindi, Western Downs, Toowoomba, Lockyer Valley and the Scenic Rim. We're doing type 1 energy assessments with that program, with walkthrough assessments and giving people some carbon advice. So farms that are keen to participate will get an energy and carbon action plan at no cost. So please get in touch with the QFF Energy team if you're in one of those areas, and we can help you with that. The next webinar is coming up. We're hoping to do one on energy efficiency opportunities and piggeries. We're yet to lock a timing for that, but our next one that we've got locked in is with Phil Szabo from the Saturn Engineering Group about large pumps, and Phil's been to quite a few farms that have large diesel and electric pumps for irrigation, so he'll be able to give us some really good information on those. And we've got 2 other ones coming up after that. One's about scheduling energy consumption to maximise your solar, and you may remember Stephen Sutar from a microgrids webinar we did a year or so ago. And also Alan Day, who's done some work with us on aquaculture, and he'll be talking about how voltage, power factor and VSDs a big piece of the energy management picture on barramundi farms, and in fact other farms that have large inductive loads and cold rooms and things too. So very relevant to a range of sectors. We also have the Energy Information Service for landholders, and any landholder or farmer in Queensland can call our QFF Energy team and ask any questions. We can talk about tariffs, energy efficiency, and farms or properties that are having been approached by renewable energy developers or energy infrastructure development. We can give some advice and point you in the right direction to get the information you need for that. So the phone number's there. It's available during business hours, and we'd be happy to help if you'd like to call us with any questions. And with that, I think we're done for the day. So thanks again very much, Ryan, for your time. That was absolutely fantastic information. Look forward to hopefully a lot of people will get to see this online. Thank you very much. Thanks also to Jonathan. It's been great to have your help, and Jonathan's a member of our energy team. So if you do get in contact with us for some help with EnergySQ or the Energy Information Service for Landholders, there's a good chance you'll get to have a chat to Jonathan as well. Been great to have you on board, and thank you again, and hopefully see you on one of our next webinars. Thank you again. Bye-bye.